Okay, everyone, let's get started. So, good morning, and you may see that my screen looks a bit different, and that's because I got another computer. My old computer was having some problems with the battery and stuff, so please be patient with me today because I'm using a different, I'm using this online app. It's not really as good as the old one, but I hope it suffices, okay, for the remainder of the course. Okay, so let's see. So just some notes. This is the second to last week of the course, okay? And make sure you submit your homework. Start submitting your homework corrections if you have not done so already. We don't want to overwhelm the tutors with too much to do next week. So this week is the last week of homework, and it is about complex numbers. We're also going to cover probability on Wednesday and Thursday. So today and tomorrow we're doing complex numbers. Wednesday, Thursday we're doing probability. Okay, what is the plan for next week? So the homework is due this Friday. That's the final homework assignment. Next week is really dedicated to, in terms of homework, there is no homework due, right? It's dedicated to you all doing your corrections and catching up on any missing assignments that you might have. Okay, so please submit all your corrections by Thursday of next week, and hopefully we can have them all graded by the end of the course. At the end of the course, I'm going to be looking for students in 9th, 10th, 11th, and 12th grades. So I'll be looking by age bracket. For highest scores, I have graded your geometry worksheets. I have not sent the grades back, but I've looked through those. I'm going to take those less seriously because people did not as well, but the first two in-class assignments are going to be considered. All of your quiz grades will be considered for the prizes, okay? So I want to make this distinction between the prizes, the scholarship prizes, and the Intellichoice Scholarship, okay? Sorry, I shouldn't have said scholarship. The prizes, okay, those are just for fun, and that's not much money. It's like a reward for doing well in the course. The Intellichoice Scholarship is what you get after you take the SAT. So you have to register for the SAT, and you have to go to College Board. I think I sent the website. Register for the August or September tests, maybe the October test as well. And take the test, send your score to Dr. Lee, okay? Dr. Goey, I can actually send this here. Okay, I'll send his email at the end. So send your email, send your score to Dr. Lee, just a screenshot of the score, and after Dr. Lee receives it, he'll see the score and he'll mail you a check, okay? And it's going to be like half the value of the test. Alexa said, so if you did good, okay, and you don't need to do corrections, yes, you do have to come next week, okay, because there's still quizzes next week. And so I'm just covering homework right now. I'm going to talk about content of next week in just a sec. Aditya said, if I was absent for one of the in-class assignments, can I do it and turn it? Yes, just tell me which one you're absent for. Well, I don't know if you even know. I'll just send you all of them and you can see which one you didn't do, Aditya. Just remind me, just send me an email so that I'm not going to remember. Okay, what are we covering next week? Next week, okay, and Isaac said, I just joined, what did I miss? Isaac, okay, you didn't really miss much. I'm just covering logistical things. This is the second to last week of the course, so do your homework corrections, submit them to your tutors, and be patient with me because I got a new computer. That's really all I've said, and I've described the scholarship. So there's a scholarship and there's a prize. The prizes are less money and it's coming out of my own pocket. It's just for fun, okay? And then the scholarship is like supported by Intellichoice, and you have to do the SAT, send your score to Dr. Lee to get the scholarship. And you have to pass the course, obviously. If you want to know your current grade, just ask your tutor, okay? And they'll tell you your current grade. Most people are doing pretty well. Okay, what are we covering next week? So this week, we're covering two topics, really, and they don't have much to do with each other. Today and tomorrow, we're doing complex numbers, which is a vast topic in itself. And also Wednesday, Thursday, we're doing probability and maybe some elementary statistics, okay? And next week, which is the final week of the course, here's my plan. I thought about this quite a bit. On Monday and Tuesday, we're going to do a sort of course review, okay? And so everyone is going to be required to attend. And in this review, the real goal is to just look at an SAT, practice set. I'm just going to pull a bunch of questions, maybe 30, 40 questions, and we're going to just do them together. Maybe I'll give you a minute to do each one and just do it. So this is like general review of the course. It won't just be practice. I'll give a sort of course compendium, big picture of math. And then Wednesday, Thursday, my goal, and I kind of want your feedback, okay? For the juniors, and this is going to be, I'm hoping, unless people just want to do more SAT practice, but I imagine people don't want to do that. I'm hoping on Wednesday and Thursday that we'll be doing some introductory calculus for the juniors and seniors. So 9th and 10th graders don't have to attend. Okay, so Monday, Tuesday, everyone. Wednesday, Thursday, just 11th and 12th graders. Okay, and this is not on the SAT, obviously. So, but I am going to expect all the 11th and 12th graders to be there because it's really going to help them out as they start calculus. So I want to know how people, does anyone object to this plan? Does anyone want all of these days to be like SAT review? What do people want? Now's your chance to voice your opinion. Or on the contrary, does this sound good? Free day. Okay, Robin wants review. Matthew wants calculus. Okay, I can't make everyone happy. Okay, Alexis wants graphing. Okay, so do people want sort of a day that is like most interested, like more extended topics? Okay, all of the above. Okay, awesome. That's an easy. Okay, so maybe Monday we'll do review, Tuesday we'll do extended topics on graphing. I actually I'm using an Apple computer now, and I got this really cool. It comes with this great grapher, so we can look at graphs and things. And then Wednesday, Thursday we'll do calculus. And I'm not going to teach you all of calculus, but I'm going to introduce to you the big ideas, and it'll really help you out. Okay, great. So let's get started with the actual course content for today. Okay. So I'm going to begin the lecture by asking you, what is math? Remember, this is how we started the entire course. I asked you this question: what is math? And I think most people told me that math relies on numbers. Math is the study of numbers. And that is actually a very good way to look at math. It turns out even nature, the way we understand nature, is not in terms of vectors and coordinate systems and matrices. It's in terms of numbers. For example, when you measure something, say you're measuring a car, okay, going down a road, measuring the speed of a car. Okay, so here's the car. I'm not great at drawing these things, but okay, and it's going, right? And it has some speed, right? We have this notion of velocity, right? And we denote this as a vector. Remember last week we talked about vectors, and it has some components in the X, Y, and Z direction, right? And but this is not what you measure. Anytime you have a device that measures something, like say you have a radar, right? Or a dot. You know how the police, when they stand by the side of the road and they measure your speed, what they're doing is it's a Doppler shift kind of thing, and so they're sending a light signal, right? It's really an infrared, like kind of radio wave signal, and it bounces back, and depending on the wavelength of this thing that bounces back, they know how fast you're going, right? Because they know how. So anyway, so anytime you measure something, no matter how you measure it, if you look at it or if you use one of these radar things, no, you always return a number. You never return a vector. You always return a scalar number. So nature is full of scalars, and from scalars we construct things like vectors and matrices. And vectors and matrices are a really great way to look at the world. For example, I'm sure you all have seen this equation, F equals ma. Well, these are vectors, right? But nature doesn't have an acceleration vector. Nature doesn't have a force that's a vector. It has a number associated with these things. So nature is full of scalars. Remember last time when I was asking for people's ages and we made this matrix of like 15, what, I don't know what number that is, 16, 15, 13, 17, so we constructed a matrix of people's ages, but this is something we constructed. This is not what you told me. You didn't tell me a matrix. You have an age, right? So indeed, space and time is constructed by scalars, and therefore math itself, so this is sort of a physical analog, but math itself is very much constructed by numbers or scalars. And numbers themselves consist of a big tree. And because there are different types of numbers, for example, your age. Oops, sorry. This is the part where I'm gonna have to get used to this system. For example, your age, right? Each of these things, these are what we call integers, right? But there are other numbers that are not so simple, right? And so what I'd like to do is construct a tree of all the numbers that we know. And so can people start shouting out the different types of numbers that we know? So we have scalars, right? So numbers are all scalars, right? So can we start sort of classifying numbers? So do people, okay, so how about, so what is a number like 15 or 16, like your age? Is this, what's the most specific way? Okay, so real and unreal, that's a good way to start. How about we start from sort of the bottom, okay? From the bottom of the tree here. And first you have the numbers. Just think about how you learned numbers, right? When you were in, I don't know, preschool or something, you probably learned the numbers 1 through 10. Yeah, so people were thinking very big picture, but I really want to start simple. So there are numbers like 1, 2, 3, 4, 5. These are the numbers that you've recited. Okay, sorry. These are the numbers you've recited since you were probably 2 or 3 years old. And these are what are called counting numbers, okay? And if you include 0, I'm sure some of you in preschool learned about the concept of 0. These are called, does anyone know?
So I'll give you 2 points for the assignment.
Okay, I'm gonna move people.
2.
Okay, what are the, anyway, okay, there, first of all, there are terms for all of these things. Does anyone know what, I don't even remember actually. Okay, well, anyway, there's a different class of numbers that happens when you include 0. Whole numbers, yeah, I thought that was it, but okay, it's good to have your affirmation. Yeah, these are called the whole numbers, I think, when you include 0. And then you can include the negative numbers, so like maybe in 2nd or 3rd grade you learned about negative numbers, and so this is like negative, so I'll put ellipses here, -4, -3, -2, -1, 0, 1, 2, 3, you get the point. Okay, and these are called what? What are all these numbers? What's the class? Just shout it out. You'll have to unmute yourself. Integers, good. And what's the next class above this? So this is like all positive and all negative numbers. But we can go further, right? Because we can take ratios of these numbers, right? So how about a number like 1/2? Or rational, yes. So all of these things are under the field of rational numbers, because all of these can, so rational, what does rational mean? Rational in philosophy means the thing that can be understood by reason, right? Or related to reasoning. But in math, it really means things like fractions, okay? The things that can be expressed as fraction. I'll explain the etymology of the word. But all of these are ratios, right, of integers. So rational numbers are by definition ratios of integers. And so anything that can be written as a ratio of integers is a rational number. And that's a vast breed, okay? It's a huge family of numbers. Why is it rational? Why is it called rational? Well, it goes back to the Greeks, right? So it doesn't just have to be 1 in the numerator. You can have 2, I don't know, 7s, so on and so forth, right? When I draw the brackets, this refers to a set of numbers. All of these are infinite sets. Why is it called rational? Well, that's because the Greeks, again, we talked about the Greeks last week, the Greeks loved ratios, and they thought about music, they thought about astronomy, geometry, and arithmetic, that's the quadrivium, right? They thought about all of these things as ratios. And in fact, their musical system, their tuning system, the way they tuned their lutes and things, was based on ratios. They would tune things in fourths or fifths. So those of you who know music, okay, I'll draw something simple. So a fourth, okay, is from, say, this is what note? Does anyone know what note this is? This is not math, but it's very relevant. Can anyone tell me? Good, E. And what note is this? Hey, good, thanks. Someone said wait. Okay, anyway, what is the interval between these two notes? Does anyone know? How many notes do you need to go? So E?
A whole step.
It's not a whole step. A whole step would be E to F sharp. It's okay, this is not math. But anyway, the Greeks, this is called a fourth, okay? And the Greeks called it a tetrachord, the interval of tetrachord. And to get from here to here, or to get from A to E, that's going down a fifth. So this is going up a fourth, and this is going down a fifth. Anyway, the Greeks knew that to go from a root to a fifth, you would multiply your frequency by 3/2. And to go from here to here, you would multiply by 2/3, well, actually 4/3 here because they're going up. So these are all ways, so the Greeks tuned their entire, all their music was based, this is called just tuning, right? Just tuning. And it was all based on ratios. And this is actually no longer the way we tune our instruments. We tune based on an irrational system. But the rational system is rooted, okay, and this is an example of music, but the rational system is very much rooted in the idea that the world can be expressed by the ratios of integers. In other words, the world can be expressed by rational numbers. So that's why it's called rational, okay? Any questions about this? This is just an example. Don't worry if you didn't understand. Okay, and then there's this entire other breed of numbers. So first of all, before we talk about, and we already know that they're irrational numbers, but before we get into irrational numbers, I want to talk about the fact that all of these things, counting numbers, whole numbers, integers, all of these things belong in the category of rational numbers. And all of these things are an infinite set of numbers, right? 1, 2, 3, 4, 5, you can go on to infinity. 0, 1, 2, 3, 4, 5, you can go on to infinity. So on and so forth, right? These are also an infinity. But notice that this infinity is this infinity for counting numbers. This is smaller than this infinity, right? And that is smaller than this infinity because this has more numbers, right? Than this one. And whole numbers have more numbers than this one. So the size of the infinity is different. So we all denote, the size or the length. For those of you who think of computer science, the length of you could think of this as a string or a tuple, and the length of this tuple is infinite, but its size is, in a sense, bigger, right, than the length of this tuple. Anyway, when you get to rational numbers, this is not just a bigger infinity, but it's a more dense infinity, right? Because now you're taking ratios of numbers. So take just the set 0, 1, 2. These are all integers, right? For rational numbers, you can create, all of these numbers are rational, but for rational numbers, you can add 1/2, 0/2, that's the same thing as 0. But anyway, you have an additional number, and you can do this for any of the numbers, right? 0, 1, 3, 0, 1, 4, and therefore this is a more dense infinity, and that has profound consequences. The fact that rational numbers are a more dense infinity, really, and a larger infinity, has profound consequences on just the way numbers work. Okay, so what are irrational numbers? Can someone give me, so if rational numbers are numbers that can be written as fractions, what logically are irrational numbers? Anyone?
Numbers that can't be written as fractions.
Yes, very good. Yeah, I'm not being sarcastic. Really, that's good. And that's exactly the definition, numbers that can't be written as fractions. And so can someone give me an example? We talked about one extensively last week.
Pi.
Yay, that's the classic example. And the Greeks were so intent on writing things as ratios, like through their music system and through just the way they understood the world, that they so desperately wanted to approximate pi. And I gave you some of these approximations. There's a famous 122/7, and then Ptolemy had one. I forgot the Ptolemy. Ptolemy was a great mathematician and astronomer, and he had his own. I think it was like 300 and something over something. Anyway, we talked about that last week. So they were desperate to express pi as a ratio, and they weren't able to because pi is just not a ratio of two real numbers. And there are a huge class of irrational numbers, and generally the square root or the cubed root, not generally, but the cubed root, the square and cubed root, and the nth root of numbers of integers often are irrational. For example, the square root of 2, the square root of 3. All of these things are the square root of 5. All of these are irrational numbers. And therefore, you can use your imagination and realize that irrational numbers are an even denser infinity than rational numbers, right? Because for every rational number you have, for example, here's our set of rational numbers, like 1/2, 1/3, 1/4. Well, you can take the square root of all of these numbers. You can take the cube root of all these numbers. So from here, you can come out with so many options, right? You can come out with the square root, right? You can take the square root of all of these, and you can take the cube root of all of these. Okay, this gives you a rational number. Anyway, the irrational numbers are an even denser infinity than rational numbers. Okay, great. So does anyone have any questions about irrational numbers, real numbers, whole numbers, integers, counting numbers? These are the 4 breeds of numbers you know of so far. Any questions about anything?
No.
Okay, no. Okay, so what do both of these numbers have in common? Irrational and rational numbers. We said that irrational numbers can't be written as fractions of real numbers. Sorry, can't be written as fractions of integers. Rational numbers are numbers that can be written as fractions of integers. But what do they both have in common? It's actually not. It's not a very intuitive thing.
They're a real number.
Yeah. So the parental sort of category is that these are real numbers, and it actually turns out that they don't have much in common aside from the fact that they all live on the line, on the number line. So if I drew a line, right? Sorry, this you can see where this app is really not as good as the other one. If anyone has suggestions for a whiteboard app for Mac, I would greatly appreciate it. You can tell me at the end. Okay, what do all these numbers have in common? Well, they all exist on this line. Okay, so I'll call this the x-axis. Okay, and here are your normal numbers. We often use integers as our scale, but just last week we were using numbers like pi as our scale, right? So all this to say, you can pick, you can plot rational and irrational numbers on the number line. What about numbers that don't, are there numbers that don't exist on the number line? That is the next question.
Imaginary numbers.
Imaginary numbers, yes. So this is one sort of branch of this tree of numbers. And then there's this other, okay, so I'm gonna zoom out so you can make out this tree. Okay, so do people see this? I don't wanna reveal the next real part. So we started, wow, this app sucks. Okay, we started with numbers, right? And then this branched into, so we worked from the sort of the bottom up, and here's one branch of the tree into real numbers. And here are sub branches, right? Each of these was its own branch. And anyway, so you get the point. Irrational numbers was a big branch. So it's an upside down tree that we're looking at. And now it turns out that there's a whole different branch, right? And that branch consists of the imaginary numbers. And so what is an imaginary number? Well, an imaginary number is a number that contains, can anyone tell me?
I.
I, and what is I?
The square root of -1.
Yes, so I is defined to be, and this is the 3 bars that mean define, right? to be the square root of -1. And this seems kind of ad hoc, kind of random to you all who have not seen this before, but what is the value of defining an entire other class of numbers that contain this value I? Well, it turns out that you might remember some definitions earlier in the course. So again, this is the definition of I. You might remember the definition of absolute value, right? People remember this definition, right? This is one of the 3 definitions of absolute value. The absolute value of something is defined to be the square root of the square of some number. And it turns out that the absolute value is actually negative when you have an imaginary number as x. So for example, when I pick x to be I, okay, let x equal I, then, and this is, square root of -1. Well, when I square the square root of -1, right, what do I get? This is I squared. What do I get? Say x was 2.
-1.
Yeah, you get -1. The reason, for those of you who are confused, if I have, say x is the square root of 2, okay? Then what is x squared? Well, it's just square root of 2 times square root of 2. What happens when you have, and I could just write this as, this squared. The square root and the square are opposite. They're inverse functions, basically, of each other, and they cancel each other out, so to speak. So it gives you 2. And similarly, when you square I, this is the same thing as square root of -1 times square root of -1. Sorry, that's exactly what I wrote. This is the same thing as, sorry, I'm having a hard time here with this. This is the same thing as this, right? And the square and square root cancel out, and they give you -1. So yes, so and therefore the absolute value of I, the absolute value of the absolute value of I is -1, right? So all of a sudden now we've opened the door to letting the absolute value be a negative number. Remember earlier in the course when I said we were dealing with real numbers, the absolute value would always be a number greater than 0, right? You can't, this thing, if you take the absolute value of any real number x, this is always greater than 0. But now we've taken the absolute value of an imaginary number, and this can be greater than 0 or less than 0, right? Okay, so that's the sort of that's the sort of algebraic novelty to imaginary numbers. Graphically, though, remember when I said that this was the number line, right? So these are our numbers 1, 2, 3, 4, so on and so forth. Graphically, the imaginary axis, the imaginary numbers correspond to a plane to a line that is perpendicular to the line of real numbers. Okay, so remember when I said, can anyone think of numbers that don't lie on this line? Well, the answer is imaginary numbers, and the way we plot it is as a line of numbers. So another number line that's very much like this first number line of real numbers, but that is perpendicular. So this is a 90-degree angle. That is perpendicular to the line of real numbers. And it's the same, it's identical, except everything is scaled by I, so to speak. Everything on this axis here, this vertical axis, is multiplied by I. So instead of 1, 2, 3, 4, you have 1i, 2i, 3i, 4i, so on and so forth. And what is the real utility of this? Well, it turns out, okay, first of all, the utility of this is like definitional, right? And so you can graph all your imaginary numbers here and all your real numbers here. So first of all, this is a definition. But the utility, right, the real inspiration is that a wave, remember sine and cosine, right? It turns out sine and cosine, remember sine of x, cosine x, these things, remember when we drew the unit circle and we found the various values of sine and cosine in these different quadrants, and then we plotted them on a graph? Well, that's exactly what's going on here. You can model sine and cosine using real and imaginary numbers. And you can project this unit circle on this plane here. Here's my unit circle. And it so turns out from your, this is beyond the scope of this really, but when you plot sine and cosine, right, you get things like this. These numbers here, these y values, correspond to the real axis, okay, right? And so, for example, this point here, for sine, this is pi. This point here corresponds to when I equals 1 and when the real axis is 0. And so, so in a sense, sine and cosine, right? This is motion on a circle, or you could think of a sphere. Motion on a circle is simpler, projected on one axis. So if I had an object that was going here and here and then back and forth, and I had a light here and I was shining light on this wall, so there was a wall here, the motion would be it would go here and then it would stop and then it would start going back and then it would stop and then it would go back and it would stop. And you can see that this motion is a sinusoid. This is called simple harmonic motion. But anyway, it can be modeled very well by using the real and imaginary. This is actually called the complex plane. It can be modeled well using this plane. And scientists often like to, instead of writing sine and cosine, they like to write this as an exponential. And this is really beyond the scope of the course, but as a complex exponential. Okay, this is your frequency and this is time. So, okay, so imaginary numbers have graphical value and they have algebraic value. And to you, they will probably seem a bit random, right? These results seem very sort of not essential to your understanding of nature, but I think one great application is in the quadratic formula, okay? In the quadratic formula, first of all, can anyone recall to me what the quadratic formula is? Someone tell me without looking it up. Shout it out. Okay, thanks, Adi. You can talk in the microphone. Like, okay, I feel like that's easier than thanks, but oh, your mic is broke. Okay, okay, it's minus b plus or minus the square root of b squared minus 4ac over 2a. And what is this thing called?
Discriminant.
Yes, and what happens when the discriminant is less than 0?
No real solution.
Yes, and so now you can see the meaning of no real solutions. When the discriminant is less than 0, you have no real solutions, but you do have imaginary solutions, right? Say your discriminant it comes out to be some square root of some negative number, right? Sorry, the discriminant is less than 0. So I'm going to pick -4 as this number, right? Say b squared minus 4ac is -4. Well, then your solution, right, is going to have some I in it, because I could write square root of -4 as square root of -1 times square root of 4, right? Everyone agree this is totally fair algebraically? And then square root of -1 is defined to be I, right? So this thing is I by definition, and square root of 4 is 2, so this is 2I. And indeed, when your discriminant is negative, this leads to x-intercepts that are generally complex, or that complex meaning having imaginary components to them. Okay, so okay, so you can see where okay, let's do an example. So this makes more sense. For example, solve y equals x squared plus 4. Can people do this? I'll just use the quadratic formula. Okay, so what is b? So what is a here? Remember your general form, ax squared plus bx plus c. What is a here?
1.
What is b?
0.
What is c?
4.
Yeah, and so I'll plug this all in the quadratic formula so you don't even have to think about it. So the x-intercept is minus b, so that's 0, plus or minus square root of b squared, that's 0, minus 4ac, that's just 16, right? Minus 4ac, so minus 16. And 2a, well, 2 times 1 is 2. And so plus or minus, well, here I have, I could again write this, I could factor out the square root of -1, and this is what, 4i over 2, so plus and minus 2i, right? So does this make sense? So your x-intercept does not have a, it's not real, it's imaginary. And how graphically, what does this correspond to? Someone It's okay, I don't know what happened. Okay, graphically, what does this correspond to? Well, let me show you. I'm gonna just share my entire desktop. Okay, people can see this. Graphically, what does this mean? Okay, I'm gonna try to use this grapher. This is so annoying. One sec here, people. Sorry. How do I do this? You can tell I'm not a skilled Mac user yet. Graphically, okay, I'm gonna graph, let's see, 2D graph. X squared plus 2, plus 4, right? Where is it? Why is it not graphing? This is so strange. Do people? Okay, this is, there it is. I was just looking. Okay, okay. Anyway, x squared plus 4. Here's the x-axis. That's actually funny because this is exactly what I was trying to say. Here's the x-axis. Remember that our notion of the intercept is where the graph crosses the x-axis. Does this graph cross the x-axis? No, not at all. Right? So see how it goes up and up. See, doesn't cross the x-axis, and therefore your solution. This thing does have solutions, but not in the real. Not along this line. Right? This is your line of real solutions, and not along that line. So this is the meaning of. This is the graphical meaning of having an imaginary root. It means that you don't have a root in the real plane, but you have a root in the imaginary. Okay, so I feel this was sort of a haphazard introduction to imaginary numbers. It's really a vast field, and it's hard for me to convey to you what this means, right? Because there are so many. Okay, so we talked about algebraically how it destroys our notion of absolute value being positive. We talked about its application. We talked about the complex plane, right? This thing is called the complex plane, and you can plot you can plot complex numbers, which is a combination of imaginary and real numbers, anywhere here on this plane, and how this is really great at modeling sine and cosine uniform circular motion, right? We talked about how, and we talked about the fact that your roots of a quadratic can be imaginary. Okay, so do people have questions about this before we go on? Please be very honest. I feel.
No.
No, and I just lost my. Sorry for the technical difficulties I'm having here. Not used to this computer. Okay, no one has questions. Okay, so what happens when you square I? We talked about this already. What happens when you square I?
You get -1.
You get -1, and we already discussed this, but this is because this is -1 squared and -1 squared. The square and the squared are opposites, so to speak, right? They cancel each other out, and this gives you -1. Okay, so it turns out that there's a huge pattern here, okay? And let's sort of derive that pattern. So what happens if I cubed I? Well, I cubed is just I squared times I. Everyone agree, right? From our discussion of, exponent rules. Wow, I'm really having a hard time here. Does everyone agree that this is true? That I cubed is I squared times I to the 1?
Yes.
Yes, because when you have the bases the same, the exponents add. And what is I squared? Well, we just found that I squared is -1, and I to the 1 is just I, and -1 times I is just -I. So it turns out that I cubed is -I, right? And now I'm going to take I to the 4th. So you can see I'm just making this list of powers of I. I to the 4th is, well, one way to break it up is I squared times I squared. Does everyone agree? Right? I squared, so the bases are the same, so they add. And I squared is just -1. Again, I squared is -1. And -1 times -1 is 1. And so this is a very fundamental result that I to the 4th is 1. And anytime you see I to the 4th, you should immediately think 1. Anytime you see I squared, you should immediately think 1. I cubed, -I. Okay, now, so do these results make sense? I squared, I cubed, I to the 4th.
Yes.
Great. what happens now if we take greater powers of I? Am I going to get anything different, or am I going to get
It'll be a repeating power,
a repeating pattern? Yeah, it's a repeating pattern, and the reason is that I to the 5th, I can write that as I to the 4th times I, right? The bases are the same, so I can add the exponents, right? So I to the 4th times I to the 1, 4 plus 1 is 5. Okay, what is I to the 4th? Well, I to the 4th is 1, and I to the 1 is just I, so this is just I. And so I'm back at where I started, right? This is the same thing as, so I to the 5th is the same thing as I to the 1. Back where I started. I started this entire thing with I to the 1, right? What about I to the 6th?
Same thing as I squared.
Yeah, it's the same thing as I squared. The reason being, you could break this into I to the 4th times I squared. I to the 4th is again 1. I squared is -1, right? So 1 times -1 is -1, obviously. And so this is equal to I squared. And you can see, it doesn't take a genius to realize that I to the 7th is the same thing as I cubed. I to the 8th is the same thing as I to the 4th. And, so I to the 4th is 1. I cubed, you can just look up in our previous results. I cubed is -I. So this pattern is, you only need to know the first four, you only need to know the first four parts of this pattern. You only need to know I squared, I cubed, and I to the 4th. And then it repeats, right? So I could ask you, so in a sense, it's a modular system. So you start with I to the 1, right? I squared. It's like a clock almost. I cubed, I to the 4th, right? And so think of this as a clock that only has 4 spots on it, like 4 hours, right? And then it repeats. So this is the same thing as I to the 5th. This is the same thing as I to the 6th. This is the same thing as I to the 7th. This is the same thing as I to the 8th. And then you can go on, right? This is the same thing as I to the 9th. This is the same thing as, can anyone tell me what this one would be?
I to the 10th.
Yep. And then this is the same thing as I to the 11th. This is the same thing as I to the 12th. On and on and on, right? This is the same thing as I to the 13th. Okay, I trust that you people don't need me to go on. But this is really what's happening, right? And if you think of it as this is called a modular system, right? And if you think of it as a clock, you'll never get these things wrong. So I could ask you, what is I to the 36th? And you should be able to tell me what this is without going through this clock, right? You should be able to tell me which one of these 4 values it is. You have a 1 in 4 chance. Yeah, it is 1. And if you guess, you have a 1 in 4 chance of getting it right. That's the good thing, right? Your odds are not terribly low. And it is 1, and the reason it's 1 is you could write this as I to the 4th to the what power?
9th.
Yes. And I to the 4th, you could break this down further. I to the 4th is 1. Well, you don't need to. I to the 4th is 1, and 1 to the 9th power is obviously 1. Similarly, I could ask you, what is I to the 100th? Can anyone tell me?
Also 1?
It is also 1, because I could write this as I to the 4th, right? To the what? To the 25th. And I to the 4th is 1, and 1 to the 25th is 1. So these are pretty easy examples, but let me give you something that's not 1, like I to the 101. It's not much harder, because you could write this as I to the 100th times I to the 1, and I to the 100th is 1, and I to the 1 is I, so this is just I. So if you were to look at the clock, this is in a sense, it's at the 12 o'clock position, I to the 101th, right? And I to the 100th is in the 9 o'clock, whatever you want to call it, right? So, okay, so does this make sense? So I should be able to ask you anything, any ridiculous number, right? Like I to the, right? 10,003 power. And this is actually really easy. That I could write this as I to the 10,000 times I to the 3. And I to the 10,000, well, that's just I to the 20, that's just I to the 4th to the 2,500 power. This is just factoring 10,000, right? And I to the 3 is negative I. And so I to the 4th, that's 1. 1 to the 2,500 is 1 times negative I gives you negative I. Okay, so I hope this makes sense. You have a 1 in 4 chance of getting it right, so to speak. So it's not hard. It just takes some getting used to. Okay, so does this make sense to people? Does anyone have any questions about the powers of I?
No.
No one? Okay, great. Okay, so I think I'll send out the quiz. Tomorrow we're going to talk about one last topic regarding complex numbers, and then I'm going to. That's not going to take all of our time, so I'm going to introduce another topic to be determined, something interesting, and then Thursday we'll start probability. Wednesday we'll start probability. So I'm going to send out the quiz. I hope today was not. Yes, I to the 2020 is 1. So okay, so generally, if you think of, that's a good way to think of it. If you think of the number I to the nth power, if n is divisible by 4, right? If n is divisible by 4, then your number is immediately 1, right? Just like I to the 8th is divisible by 4, I to the 2020 is divisible by 4, I to the 1,000 is divisible by 4, then your number is 1. And the reason is that you could write this as I to the n over 4. So I to the 4th times n to the 4, right? I to the 4th is 1, and then n to the 4 is some integer, and 1 to some integer is 1. If n is not divisible by 4, then you will generally have I, negative I, or negative 1 as your answers. Okay, I hope this makes sense to people. I hope this wasn't too haphazard. The grapher on, yes, Aditya. Okay, so Aditya mentioned me privately, and he said the grapher on Mac is really great for 3D graphs, and I was messing with that yesterday. So we'll work with that tomorrow. In the meantime, let's send you your quiz. Give me a sec, people. Thanks for your patience today, as I was getting used to this computer. Okay, I just sent it in the chat. Let me know if you have luck. Why did you not have meetings on Wednesday and Thursday? Isaac, I did. You must have missed. Like last week? Yeah, we met last week. I might have forgotten to send out the link or something, but we met. Okay, sorry. Okay, my bad. I'll send you the YouTube page for the lectures. What am I saying? So I'll post today's. There you go. So Isaac, yeah, you're welcome. I should stop recording. This is not.